picture this. You are inside a spaceship. The engines have been roaring for months, pushing you faster and faster through the emptiness of space. You have left Earth behind. You have left the Moon behind. You have passed Mars, Jupiter, Saturn. You are now in the void between stars. Nothing around you. No planets, no moons, no asteroids. Just darkness in every direction, stretching for trillions of kilometers. And now, you want to stop. You reach for the controls. You want to hit the brakes. But here is the terrifying truth. There are no brakes. There is nothing to push against. There is nothing to grab onto. There is no friction beneath you. There is no air around you. There is no surface to dig into. You are moving at 50,000 kilometers per hour, and the universe does not care. It will not help you slow down. Not even a little bit. And this is not science fiction. This is the actual, real, calculated, verified, tested reality of spaceflight. Stopping a spaceship in deep space is one of the most difficult challenges in all of physics and engineering. It is so difficult that most of our space missions are designed specifically to avoid it. We send probes that fly past their targets because we simply cannot afford to stop them. We design missions around the assumption that stopping is either impossible or so expensive that it changes the entire architecture of the spacecraft. Today, we are going to explore this problem from every angle. We are going to understand why something so simple on Earth, something you do every time you press the brake pedal in your car, becomes almost impossible once you leave our planet. We will dive into Newton's laws and see them in a way you have never seen them before. We will wrestle with the rocket equation, that brutal mathematical relationship that makes engineers weep. We will look at real missions, real spacecraft, real failures, and real successes. We will push into the realm of interstellar travel and discover why the stopping problem might be the single greatest barrier to human expansion across the galaxy. We will touch relativistic physics, quantum effects, thermodynamics, and engineering limits. And by the end, you will understand something profound about the nature of our universe. A universe that lets you move freely, but charges an enormous price for standing still. But before we go deep into the physics, let me tell you a story. A real story. A story about a spacecraft that had to stop, and what it took to make that happen. And another spacecraft that tried to stop and was destroyed because of the tiniest mathematical error imaginable. On August 10, 2005, NASA launched the Mars Reconnaissance Orbiter from Cape Canaveral, Florida. This spacecraft had one primary mission: get to Mars, enter orbit around Mars, and then study the planet in extraordinary detail using the most powerful cameras and instruments ever sent to another world. The journey to Mars took about 7 months. During that time, the spacecraft was essentially coasting, moving through the vacuum of space at enormous speed after its initial launch boost. By March 10, 2006, it arrived in the vicinity of Mars. And here is where the problem begins. The spacecraft was approaching Mars at approximately 3 kilometers per second relative to the planet. That is about 10,800 kilometers per hour. At that speed, if you do nothing, you fly right past Mars and vanish into the solar system, lost forever in a solar orbit that will never bring you back. You get one chance. One single chance to slow down enough for Mars's gravity to capture you into orbit. Miss that window, and the entire mission, the entire billion-dollar investment, years of planning, thousands of engineers' work, all of it is gone. So what did the Mars Reconnaissance Orbiter do? It performed what is called a Mars Orbit Insertion Burn. For exactly 27 minutes, the spacecraft fired its main engines in the opposite direction of travel. Think about that. 27 minutes of continuous engine firing. not a quick tap of the brakes. 27 straight minutes of burning fuel at maximum thrust. And in those 27 minutes, the spacecraft consumed 1,190 kilograms of fuel. That is more than 1/3 of all the fuel it carried for the entire mission. 1/3 of its fuel budget, gone in 27 minutes, just to slow down enough to be captured by Mars's gravity. But here is the thing that makes this even more remarkable. That burn did not actually put the spacecraft into its final orbit. After 27 minutes of burning more than 1,000 kilograms of fuel, the spacecraft was only in a very large, elongated orbit around Mars. It was captured, yes, but it was nowhere near its working orbit. To get into its final tight orbit around Mars, the spacecraft then had to perform a process called aerobraking. Over the next 6 months, from March 2006 to November 2006, the Mars Reconnaissance Orbiter dipped into the thin upper atmosphere of Mars 445 times. 445 individual passes through the atmosphere, each one using atmospheric friction to slow the spacecraft down by a tiny amount. Each pass carefully calculated. Too deep, and the spacecraft burns up. Too shallow, and no slowing occurs. 6 months of the most delicate orbital mechanics, just to complete the stopping process. Now think about what this means. Even with a planet's atmosphere to help, even with a massive gravity well to exploit, stopping required 27 minutes of burning 1/3 of the spacecraft's fuel, plus 6 months of additional careful maneuvering. This was stopping at Mars, a planet right next door in cosmic terms. A planet with an atmosphere you can use for braking. A planet with significant gravity. In deep space, between the stars, there is nothing. No atmosphere. No gravity well to capture you. No friction. Nothing at all. And if you want to understand how critical and unforgiving this process is, let me tell you about another spacecraft. The Mars Climate Orbiter. Launched on December 11, 1998, this spacecraft was designed to study the Martian atmosphere from orbit. It too had to perform an orbit insertion burn to slow down and be captured by Mars. On September 23, 1999, it arrived at Mars and began its deceleration burn. And then, it was lost. Destroyed, gone. Why? Because one team of engineers had calculated the thrust data in pound-force seconds, an imperial unit, while the navigation software expected the data in Newton seconds. A metric unit. That is it. A unit conversion error. Pounds versus newtons. The result was that the spacecraft approached Mars at the wrong angle during its deceleration maneuver. Instead of passing through the upper atmosphere at a safe altitude, it dipped too deep, entering denser atmosphere than its heat shield could handle, and it either burned up or broke apart. A $327 million spacecraft, years of work by hundreds of brilliant engineers, destroyed because the deceleration phase is so precise, so unforgiving, that even a tiny mathematical inconsistency means total failure. These stories illustrate something fundamental. Stopping in space is not like stopping on Earth. It is an entirely different kind of problem. It is a problem so severe, so deeply rooted in the basic laws of physics, that it shapes everything about how we design spacecraft, plan missions, and think about the future of space exploration. Let us now understand exactly why. If you are finding this fascinating, and I promise you it only gets more incredible from here, take a moment to subscribe to this channel. We go deep into real space science, no speculation, no fiction, just the actual physics of the cosmos explained in a way that makes you think differently about reality. Hit that like button and leave a comment telling me whether you think humans will ever solve the stopping problem for interstellar travel. Now, let us continue. To understand why stopping in deep space is so difficult, we need to start with the most fundamental laws of motion. Laws so familiar, so seemingly simple, that we often forget how radical they truly are. Newton's first law of motion states that an object in motion stays in motion at the same speed and in the same direction unless acted upon by an external force. On Earth, this law seems obviously wrong. Everything around us eventually stops. Roll a ball on the floor, it stops. Throw a paper airplane, it eventually falls and stops. Slide a book across a table, it stops. Kick a football, it stops. Everything stops. So how can Newton say objects stay in motion forever? The answer is friction. Air resistance. Gravitational drag. Every time something moves on Earth, countless invisible forces are working against it. The ball on the floor experiences rolling friction from the surface and air resistance. The paper airplane fights against air molecules and gravity. The book on the table fights against surface friction. These forces are so ever-present on Earth that we have evolved to think of stillness as the natural state and motion as something that requires continuous effort. But in deep space, all of those stopping forces vanish. There is no air to create drag. There is no surface to create friction. Gravitational effects from distant objects are immeasurably weak over interstellar distances. In deep space, Newton's first law operates in its purest, most naked form. An object moving at 50,000 kilometers per hour will continue moving at 50,000 kilometers per hour. Not for a minute, not for an hour, not for a year, forever, literally forever, until the heat death of the universe billions upon billions of years from now. That object will still be moving at 50,000 kilometers per hour if nothing acts upon it. This is not an exaggeration. This is not a simplification. This is the literal, verified, mathematical truth of physics in a vacuum. Voyager 1, launched on September 5, 1977, is currently traveling through interstellar space at approximately 17 kilometers per second. That is about 61,200 kilometers per hour. It will never stop. There is nothing in its path for light years that could slow it down by any meaningful amount. In approximately 40,000 years, it will pass within about 1.6 light years of the star Gliese 445 in the constellation Camelopardalis. It will not stop there. It will fly past at the same speed it has now and continue into the galaxy for millions, potentially billions of years, gradually drifting through the vast emptiness between stars. Voyager 1 is a monument to Newton's first law. It is proof that in the void, motion is eternal. Now let us consider what this means for stopping. If motion is the natural, permanent state in space, then stopping requires fighting against this fundamental tendency of the universe. You must apply a force to counteract your velocity. You must push in the opposite direction of your travel. And this is where Newton's third law becomes critical. Newton's third law states that for every action, there is an equal and opposite reaction. This is how rockets work. A rocket does not push against the air or the ground. A rocket works by throwing mass out the back at high speed. The reaction to that expelled mass is a force pushing the rocket forward. It is like standing on a frozen lake with zero friction and throwing a heavy ball. As you throw the ball one way, your body moves the other way. That is what a rocket does. It throws molecules of exhaust gas backward at tremendous speed, and the reaction force pushes the rocket forward. Now here is the critical point for stopping. To slow down in space, you must do the exact same thing, but in reverse. You must throw mass in the direction you want to go, meaning forward, so that the reaction force pushes you backward, slowing you down. In practical terms, this means you must turn your spacecraft around so that your engines point forward, and then fire them. You are now pushing exhaust gases in your direction of travel, and the reaction slows you down. This is called a retrograde burn or deceleration burn. The physics is beautiful in its symmetry. The same mechanism that speeds you up can slow you down. Just point it the other way. Simple, right? Not even close. Because here is where the nightmare begins. Every molecule of exhaust you throw forward to slow yourself down is a molecule you had to carry with you from the beginning of the journey. It is fuel. And that fuel has mass. And that mass had to be accelerated along with the rest of the spacecraft when you started your journey. Which means you needed more fuel at the beginning just to carry the fuel you would later use for stopping. Which means more mass to accelerate at the start. Which means more fuel needed. Do you see the spiral? This is the most fundamental problem in all of rocketry. It is so central, so devastating, that it has a name. It is called the Tsiolkovsky rocket equation, and it is the reason why stopping in deep space is almost impossible. In 1903, a Russian schoolteacher and self-taught scientist named Konstantin Tsiolkovsky published a paper that would define the limits of space travel for all time. In this paper, he derived a mathematical relationship that describes how much velocity change a rocket can achieve based on how much fuel it carries and how fast that fuel is expelled. The equation is this. Delta V equals the exhaust velocity multiplied by the natural logarithm of the ratio of initial mass to final mass. Let me explain each part. Delta V is the total change in velocity the rocket can achieve. It is your budget of speed change. You can use it to speed up, slow down, change direction, whatever you want. But once it is spent, it is gone. Exhaust velocity is how fast your fuel leaves the rocket. Different types of engines have different exhaust velocities. Chemical rockets typically have exhaust velocities around 3 to 5 kilometers per second. Iron engines can achieve 20 to 50 kilometers per second, but with very low thrust. Nuclear thermal rockets might achieve 8 to 10 kilometers per second. The initial mass is the total mass of the spacecraft at the start, including all fuel. The final mass is what remains after the fuel is burned, basically the spacecraft itself without fuel. And then there is the natural logarithm. This mathematical function is where the tyranny lives. The natural logarithm grows very slowly. To double your delta V, you do not need to double your fuel. You need to square your fuel ratio. To triple it, you need to cube your fuel ratio. The relationship is exponential in reverse. This means that small increases in required velocity change demand enormous increases in fuel mass. Let me give you concrete numbers to illustrate this nightmare. Suppose you have a chemical rocket engine with an exhaust velocity of 4.5 kilometers per second. This is typical for the best chemical rockets we have today, using liquid hydrogen and liquid oxygen. Now suppose you want to achieve a total delta V of 9 kilometers per second. Using the rocket equation, your initial mass must be about 7.4 times your final mass. That means for every 1 kilogram of spacecraft, you need 6.4 kilograms of fuel. Challenging, but possible. This is roughly what the space shuttle achieved. Now suppose you want 18 kilometers per second of delta V. Double the velocity change. Do you need double the fuel ratio? No, you need the ratio squared. 7.4 squared is about 55. For every 1 kilogram of spacecraft, you now need 54 kilograms of fuel. That is 54 times the mass of your payload in fuel alone. Want 27 kilometers per second? The ratio cubes. 7.4 cubed is about 405. 405 kilograms of fuel for every 1 kilogram of spacecraft. And for 36 kilometers per second, 7.4 to the fourth power, about 3,000. 3,000 kilograms of fuel per kilogram of payload. The numbers explode exponentially. This is the tyranny of the rocket equation. Now apply this to our stopping problem. If you want to accelerate a spacecraft to a certain speed and then stop it at the destination, you need delta V for speeding up and delta V for slowing down. The total delta V is doubled. And because of the exponential nature of the rocket equation, doubling your delta V does not double your fuel. It squares your fuel requirement. Let me walk through this with real numbers. Imagine a mission where you need to travel at 20 kilometers per second to reach your destination in a reasonable time. With chemical rockets at 4.5 kilometers per second exhaust velocity, just accelerating requires a mass ratio of about 86:1. 86 kilograms of total initial mass for every 1 kilogram of final spacecraft. That is already extreme. Now add stopping. You need 20 kilometers per second to speed up and 20 kilometers per second to slow down. Total delta V is 40 kilometers per second. The mass ratio for this is e to the power of 40 divided by 4.5, which is e to the power of 8.9, which is approximately 7,300. 7,300 kilograms of fuel for every single kilogram of spacecraft that arrives at the destination and stops. Let that sink in. If you want to deliver a 1,000 kilogram probe to its destination and have it stop there, you need 7.3 million kilograms of fuel at the start. 7,300 tons of fuel for a 1-ton probe. And this is at 20 kilometers per second, which is laughably slow for interstellar travel. Proxima Centauri, the nearest star, would take 63,000 years to reach at 20 kilometers per second. Now compare this to a flyby mission, where you do not stop. A flyby only needs delta V for acceleration, 20 kilometers per second. Mass ratio of 86:1. 86,000 kilograms of fuel for a 1,000 kilogram probe. Still a lot, but incomparably less than 7.3 million kilograms. The stopping penalty is not an additive factor, it is a multiplicative explosion. This is why New Horizons flew past Pluto instead of orbiting it. This is why Voyager flew past Jupiter, Saturn, Uranus, and Neptune instead of stopping at any of them. The fuel required to stop was simply not feasible. Let me deepen this analysis further because the fuel-carrying fuel problem goes even deeper than most people realize. When you pack fuel for stopping, that fuel is dead weight during the acceleration phase. It just sits there, adding mass, requiring more fuel to push it up to speed. Let us think about this step by step. You need 100 kilograms of fuel to stop. That 100 kilograms must be accelerated to cruising speed along with the spacecraft. The fuel to accelerate that extra 100 kilograms is, let us say, another 100 kilograms. But now you have an extra 100 kilograms of acceleration fuel, which also needs to be accelerated when you first launch. So you need more fuel. And that additional fuel needs even more fuel. It is a cascading series. Each layer of fuel requires another layer of fuel to carry it. Fortunately, the cascade does converge mathematically. It does not go to infinity. But it converges to those enormous numbers we just calculated. 7,000 to 1 ratios. 10,000 to 1. For interstellar speeds, millions to 1. This is not a limitation of our current technology. This is not something better engineering will solve. This is a fundamental mathematical constraint imposed by physics itself. No matter how good your chemical rockets become, you cannot escape the rocket equation. It applies universally to any system that works by expelling mass for thrust. The only way to change the equation is to change the exhaust velocity, to find propulsion methods that throw mass out the back at much higher speeds. This is why ion engines, nuclear rockets, and antimatter drives are discussed for deep space travel. They offer higher exhaust velocities, which tames the exponential growth. But even the best theoretical propulsion systems face limits when the required delta V is large enough, and the stopping problem always doubles it. Let us now zoom out and look at how real space missions have confronted the stopping problem throughout history. The approaches taken by mission designers reveal just how central this challenge is to everything we do in space. The simplest approach, and the one used for our most ambitious deep space missions, is to simply not stop. Do not even try. Design the mission as a flyby. Accept that you will flash past your target at enormous speed and get only a brief window of observation. This was the approach for Pioneer 10 and Pioneer 11, launched in 1972 and 1973. These were the first spacecraft to travel through the asteroid belt and visit Jupiter. Pioneer 10 flew past Jupiter in December 1973 at about 132,000 kilometers per hour relative to the planet. It did not stop. It could not stop. The fuel required to decelerate from that speed would have been many times the mass of the entire spacecraft. So it flew past, took its pictures, made its measurements, and kept going. It is now somewhere beyond the orbit of Pluto, still traveling, still coasting, and it will do so forever. Voyager 1 and Voyager 2, launched in 1977, took the flyby approach even further. They visited multiple planets using gravity assists, flying past Jupiter, then Saturn, then in Voyager 2's case Uranus and Neptune. At each planet, they flew by at tremendous speed, gathering data in a brief window, then moving on. Neither could stop at any of these worlds. The beautiful images we have of Neptune's blue atmosphere, of Jupiter's great red spot, of Saturn's rings, were all captured in brief flyby windows, sometimes just hours of close approach after years of travel. This is the tax of not being able to stop. You get moments, not months, of close observation. New Horizons, launched in January 2006, was specifically designed as a flyby mission to Pluto. When it arrived at Pluto on July 14, 2015, it was traveling at about 50,000 kilometers per hour relative to the dwarf planet. The close encounter lasted approximately 1 day. After 9.5 years of travel, the spacecraft had about 24 hours of close observation of its target. Then it was gone, speeding away into the Kuiper belt, never to return to Pluto. Why didn't it stop? Because stopping from 50,000 kilometers per hour would have required a massive fuel supply that would have made the spacecraft too heavy to launch, or would have required a much larger, much more expensive rocket, or would have required decades more travel time on a lower energy trajectory. The mission designers made the economic and physical calculation and concluded that stopping was not worth the cost. Better to fly past and get brief but valuable data than to attempt an orbit and potentially fail or make the mission impossible. The second approach, and the one used when stopping is essential for mission success, is to carry the fuel and pay the enormous weight penalty. This is what was done for missions that absolutely needed to orbit their targets. Cassini, the great Saturn explorer, is perhaps the finest example. Launched on October 15, 1997. Cassini carried approximately 3,132 kilograms of fuel at launch. The spacecraft's dry mass was about 2,150 kilograms. So more than half of the spacecraft's total mass was fuel. And why so much fuel? Because Cassini needed to stop at Saturn. On July 1, 2004, after nearly 7 years of travel, Cassini arrived at Saturn and performed its orbit insertion burn. For 96 minutes, the main engines fired, consuming about 800 kilograms of fuel. 96 minutes of continuous burn, eating through hundreds of kilograms of propellant, just to slow down enough for Saturn's gravity to capture it into orbit. Without that burn, Cassini would have shot past Saturn and been lost forever in the outer solar system. But even getting to Saturn with enough fuel for the orbit insertion was a monumental challenge. Cassini could not simply fly directly to Saturn on a fast trajectory, because that would require even more fuel to slow down upon arrival. Instead, it took an indirect route, using gravity assists from Venus twice, Earth once, and Jupiter once, over the course of nearly 7 years. These gravity assists provided free velocity changes, allowing Cassini to reach Saturn without using as much fuel, preserving more fuel for the critical orbit insertion burn. The entire mission architecture, the 7-year journey. The complex trajectory bouncing off multiple planets, all of it was designed around the stopping problem. How do we arrive at Saturn with enough fuel left to stop? The Juno mission to Jupiter, launched in August 2011, faced a similar challenge. On July 4, 2016, Juno performed a 35-minute orbit insertion burn to slow down and be captured by Jupiter's gravity. This was one of the most nerve-wracking moments in the mission. The burn had to be precise. If the engines failed or underperformed, Juno would fly past Jupiter and be lost. There was no second chance. The mission team had one 35-minute window, and if anything went wrong during those 35 minutes, $900 million and 5 years of travel would be wasted. The burn succeeded. Juno entered orbit. But the razor-thin margins of that moment illustrate how difficult stopping is even at planets with enormous gravitational pull. Perhaps the most remarkable example of the stopping problem's severity is the Messenger mission to Mercury. You might think Mercury would be easy to reach. It is close to the Sun. Everything falls toward the Sun, right? Just fall inward and there you are. But this is profoundly wrong. Reaching Mercury orbit is one of the hardest things to do in the solar system, specifically because of the stopping problem. Here is why. To spiral inward toward the Sun, you need to lose orbital velocity. Earth orbits the Sun at about 30 kilometers per second. Mercury orbits at about 47 kilometers per second. But these orbits are at different distances. To fall from Earth's orbit to Mercury's orbit, you actually need to change your velocity by a tremendous amount, and then once you arrive at Mercury's distance, you are traveling at the wrong speed for Mercury's orbit and must change velocity again to match Mercury and enter orbit. The total delta V required for Messenger to enter Mercury orbit was enormous, far too much for the spacecraft to achieve with its fuel alone. So what did Messenger do? It performed gravity assists, 6 of them, 1 flyby of Earth, 2 flybys of Venus, and 3 flybys of Mercury itself. Over the course of 6.5 years, Messenger bounced around the inner solar system, using each planetary encounter to modify its velocity, slowly shaping its orbit to approach Mercury at just the right speed and angle. Only after all 6 gravity assists and 4 years of deep space maneuvers was Messenger in a position where its remaining fuel could accomplish the final orbit insertion burn at Mercury. The mission launched on August 3, 2004, and entered Mercury orbit on March 18, 2011. 6.5 years of intricate orbital dancing. All because stopping at Mercury is so phenomenally expensive in terms of velocity change. The third approach to the stopping problem, aerobraking, works only in very specific circumstances. If your destination has an atmosphere, you can use that atmosphere to slow down. By dipping into the atmosphere at a shallow angle, atmospheric friction generates drag that reduces your orbital velocity. This is essentially free deceleration. You use the planet's air as a brake pad. The Mars Reconnaissance Orbiter, as I described earlier, used this technique with 445 passes over 6 months. The Mars Global Surveyor, arriving in September 1997, used aerobraking over a year and a half with over 1,000 atmospheric passes to reach its final circular orbit. The European Space Agency's Venus Express used a limited form of aerobraking to lower its orbit around Venus. But aerobraking has severe limitations. First, the planet must have an atmosphere. No atmosphere, no aerobraking. This rules out the Moon, Mercury, most asteroids, most moons in the outer solar system, and of course anywhere in interstellar space. Second, the atmosphere must be thick enough to provide useful drag, but thin enough not to destroy the spacecraft. This is a narrow window. Third, the spacecraft must be designed to withstand repeated heating from atmospheric friction, requiring heat-resistant materials and specific structural designs. Fourth, the process takes months, sometimes over a year, during which the spacecraft is vulnerable to atmospheric variability. A sudden dust storm on Mars, for instance, can change atmospheric density and make aerobraking passes unpredictable. Despite these limitations, aerobraking remains one of the most valuable tools in a mission designer's toolkit, simply because it does not require carrying extra fuel. Now, let us leave the familiar territory of our solar system and venture outward. Let us talk about interstellar travel, where the stopping problem transforms from a serious engineering challenge into something that approaches physical impossibility. The distances between stars are so vast, the speeds required so extreme, that the stopping problem becomes the dominant constraint on everything we might dream of doing beyond our solar system. The nearest star to our Sun is Proxima Centauri, at a distance of approximately 4.24 light-years. 1 light-year is about 9.46 trillion kilometers. So Proxima Centauri is about 40 trillion kilometers away. To put this in perspective, if you traveled at the speed of New Horizons, 50,000 kilometers per hour, reaching Proxima Centauri would take approximately 90,000 years. Obviously, this is not useful for any practical mission. To reach another star in a reasonable time frame, say within a human lifetime, you need to travel much faster. If you wanted to reach Proxima Centauri in 50 years, you would need to travel at approximately 25,000 kilometers per second. That is about 8% of the speed of light. If you wanted to get there in 20 years, you need about 60,000 kilometers per second, roughly 20% of the speed of light. These speeds are staggering. They are hundreds of times faster than any spacecraft we have ever built. But let us set aside the problem of reaching these speeds for a moment and focus on our question. What happens when you arrive? What does it take to stop from these velocities? Because if you cannot stop, you flash through the Proxima Centauri system in a matter of hours or even minutes, barely glimpsing its potentially habitable planet before disappearing forever into the interstellar void. Let us calculate. Imagine a spacecraft with a mass of 1,000 kilograms traveling at 10% of the speed of light, 30,000 kilometers per second. The kinetic energy of this spacecraft is 1/2 times mass times velocity squared. That gives us 1/2 times 1,000 kilograms times 30,000 kilometers per second squared. Converting to standard units, that is 1/2 times 1,000 times 30 million meters per second squared, which equals 4.5 times 10 to the 17th joules. 450 million billion joules. This is approximately 107 megatons of TNT equivalent. This is more than twice the energy of the Tsar bomber, the largest nuclear weapon ever detonated. And this is the kinetic energy of a single small probe, just 1 metric ton, traveling at a modest 10% of light speed. To stop this probe, you must remove all of this kinetic energy. Every last joule. And in the vacuum of deep space, the only way to do this is to expel reaction mass in the forward direction, converting the kinetic energy into exhaust kinetic energy. The fuel to do this, plus the fuel to carry that fuel from the start, creates the same exponential nightmare we discussed before, but now at a scale that is truly terrifying. With the best chemical rockets, exhaust velocity of 4.5 kilometers per second, the mass ratio needed to decelerate from 30,000 kilometers per second is e to the power of 30,000 divided by 4.5. That is e to the power of 6,667. This number is so large it has no physical meaning. It exceeds the number of atoms in the observable universe by an incomprehensible margin. Chemical rockets are completely, absolutely, totally useless for interstellar deceleration. What about nuclear thermal rockets? With an exhaust velocity of about 9 kilometers per second, the mass ratio is e to the power of 3,333. Still meaningless. Still incomprehensibly large. What about ion engines with an exhaust velocity of 50 kilometers per second? The mass ratio is e to the power of 600. Still impossibly large. What about the most advanced theoretical propulsion, nuclear pulse propulsion like Project Orion, with an effective exhaust velocity of perhaps 100 kilometers per second? Mass ratio is e to the power of 300, still larger than the number of particles in the universe. What about antimatter catalyzed fusion, perhaps achieving exhaust velocities of 1,000 kilometers per second? Mass ratio is e to the power of 30. That is about 10 to the 13th, or 10 trillion. Still absurd. For every kilogram you want to stop, you need 10 trillion kilograms of fuel at the start. For our 1-ton probe, that is 10 quadrillion kilograms of fuel. 10 billion tons. Roughly the mass of a small asteroid. What about pure antimatter rockets, the theoretical ultimate in propulsion? These could achieve exhaust velocities approaching the speed of light, around 100,000 to 200,000 kilometers per second. At an exhaust velocity of 100,000 kilometers per second, the mass ratio for decelerating from 30,000 kilometers per second is e to the power of 0.3, which is about 1.35. A mass ratio of 1.35 to 1. That means you need about 0.35 kilograms of antimatter fuel for every kilogram of spacecraft. For our 1,000 kilogram probe, that is 350 kilograms of antimatter. Now this is finally in the realm of the physically meaningful. But there is a catch. Actually, there are several catches. First, the total mass of antimatter produced by all the particle accelerators on Earth in all of history amounts to roughly 20 nanograms. 20 billionths of a gram. We need 350 kilograms. To produce 350 kilograms of antimatter with current technology would require more energy than human civilization has used in its entire existence, and it would cost. At current production efficiencies, something on the order of trillions upon trillions of dollars. Second, storing antimatter is incredibly dangerous and difficult. Antimatter annihilates on contact with normal matter. Any container made of normal matter cannot hold it. You need magnetic or electric fields to suspend it in a perfect vacuum. Any failure in containment means an explosion. 350 kilograms of antimatter annihilating with normal matter would release energy equivalent to about 15,000 megatons of TNT. 15,000 nuclear bombs. One containment glitch, and you have the largest explosion in human history. Third, even if you solve production and storage, the engineering of an antimatter rocket that efficiently converts annihilation energy into directed thrust is far beyond our current capabilities. The gamma rays produced by matter-antimatter annihilation travel in all directions and are extremely difficult to focus or redirect. Only a fraction of the annihilation energy can be converted into useful thrust with any known or proposed method. So even with the most extreme propulsion system allowed by physics, stopping from interstellar speeds is barely feasible and requires technology centuries or millennia beyond our current capabilities. This is the depth of the stopping problem for interstellar travel. In 2016, a real funded project was announced that confronts this problem head-on. It is called Breakthrough Starshot. Funded by entrepreneur Yuri Milner with advisory from the late Stephen Hawking, Breakthrough Starshot proposes sending tiny spacecraft, just a few grams each, to Proxima Centauri using a massive ground-based laser array. The lasers would push ultra-thin light sails, accelerating these gram-scale probes to 20% of the speed of light. At that speed, they would reach Proxima Centauri in about 20 years. But here is the critical admission built into the very design of this project. These probes cannot stop. They will flash through the Proxima Centauri system at 60,000 kilometers per second. The entire passage through the potentially habitable zone around Proxima Centauri will take perhaps a few hours at most. The probes will take whatever measurements they can during that brief window, transmit data back toward Earth using their tiny onboard lasers, and then continue into the void forever. The architects of Breakthrough Starshot explicitly acknowledge that stopping is not possible for these probes. The energy required to decelerate even a gram-scale object from 20% light speed is far beyond what the tiny probe can carry or generate. The project accepts the flyby limitation because the alternative, trying to stop, makes the entire mission impossible with any foreseeable technology. This is the clearest, most modern, most real-world example of the stopping problem defeating our best efforts. The most ambitious interstellar mission ever seriously proposed and funded cannot stop at its destination. It can only look as it passes by. This tells us something profound about the nature of our universe and the challenges facing any civilization that wishes to expand among the stars. Let me now explore the various theoretical solutions that scientists have proposed for the interstellar stopping problem. Because brilliant minds have been working on this for decades, and their ideas, while often impractical, reveal fascinating physics. The first proposed solution is called a magnetic sail, or mag sail, first seriously analyzed by Robert Zubrin and Dana Andrews in a paper published in 1990. The concept is elegant. You deploy a large superconducting loop of wire, perhaps dozens or hundreds of kilometers in diameter, which generates a powerful magnetic field. This magnetic field interacts with the charged particles of the interstellar medium, the sparse plasma of protons and electrons that fills the space between stars. As the spacecraft plows through this medium at high speed, the magnetic field deflects these particles, and the reaction force decelerates the spacecraft. It is essentially using the interstellar medium as a very thin brake fluid. The physics works in principle. At high speeds, even a sparse medium can provide meaningful drag if you have a large enough magnetic field to interact with it. Calculations suggest that a mag sail could decelerate from perhaps 10 to 15% of light speed down to maybe 1 to 2% over a distance of about 1 to 2 light years. This is not negligible. It significantly reduces your velocity without requiring any fuel at all. The interstellar medium itself provides the reaction mass. However, there are severe problems. First, the effectiveness of a mag sail depends on your velocity. The faster you go, the more particles you encounter per second, the more drag force you experience. As you slow down, you encounter fewer particles per second, and the drag decreases. This means mag sails work well at high speeds, but become increasingly useless as you approach low speeds. They might get you from 10% light speed to 1%, but going from 1% to 0 requires something else. Second, the superconducting loop must be enormous, possibly hundreds of kilometers across, and must remain superconducting throughout the journey. Any break in superconductivity means the magnetic field collapses and braking stops instantly. Third, the interstellar medium is not uniform. Its density varies significantly between regions, meaning your braking is unpredictable. Fourth, the interaction between the magnetic field and the interstellar plasma generates enormous heat at the boundary layer, which must be radiated away. Despite these issues, the magsail remains one of the most promising passive deceleration concepts. It requires no fuel for the braking phase itself. You just need an enormous superconducting coil and the patience to decelerate over several light years of distance. The second proposed solution comes from the legendary physicist and space visionary Robert Forward. In 1984, Forward published a paper titled Round-Trip Interstellar Travel Using Laser-Pushed Light Sails. His proposal was ingenious. You use a powerful laser positioned in the home star system to push a light sail spacecraft up to interstellar speeds. The sail is made of an ultra-thin reflective material. The laser bounces off it, transferring momentum, and the spacecraft accelerates without carrying any fuel. This solves the acceleration problem. But what about stopping? Forward's solution for stopping was brilliant and complex. He proposed that the light sail would be made of two parts, an outer ring and an inner disk. As the spacecraft approaches the destination star, the outer ring detaches. The laser from the home system continues to push the outer ring, which is now flying ahead of the inner disk. The inner disk turns around to face the ring. Light from the home laser hits the ring, reflects back, and then hits the inner disk. This reflected light pushes the inner disk backward, decelerating it. Essentially, the outer ring becomes a relay mirror that redirects the laser from the home system into a decelerating push. This is conceptually beautiful, but faces enormous practical challenges. The laser must maintain precise aim over distances of light years. The beam spreads out over such distances, requiring either impossibly precise focusing or impossibly large sail areas. The relay mirror must be precisely positioned and angled during the deceleration phase, requiring extraordinary control over a structure separated by millions of kilometers. And the energy requirements for the laser are staggering, potentially requiring the output of a small star focused into a beam. Despite these challenges, Forward's concept remains one of the few proposed methods that could theoretically decelerate a macroscopic payload from interstellar speeds without carrying fuel. It shifts the energy source to the home system rather than the spacecraft itself, which is a fundamental advantage. A third approach, proposed in various forms by multiple researchers, is to use the destination star's own radiation pressure for braking. As you approach a star, you deploy a light sail and use the star's light to push against your motion. If you approach from the correct angle and your sail is large enough, the radiation pressure from the destination star can decelerate you. This is called photogravitational braking. Research published by Ren Heller and Michael Hipke in 2017 explored this concept specifically for trips to nearby star systems. They calculated that a spacecraft could be decelerated by the combined radiation pressure and gravitational effects of the Alpha Centauri binary system. By carefully angling the sail and choosing the right trajectory, a spacecraft could use Proxima Centauri's parent stars to slow down significantly. Their calculations showed this could work for probes traveling at perhaps 4 to 5% of light speed, though the deceleration phase would require precise navigation and would take years. This approach has the beautiful property of requiring no fuel and no infrastructure at the destination. The star itself provides the braking force. However, it only works for relatively slow interstellar speeds and requires the destination to be a luminous star or star system. It would not work for travel to dim red dwarfs or to interstellar space itself. A fourth concept, more speculative but theoretically sound, involves harvesting fuel en route. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, imagines a spacecraft with a vast electromagnetic scoop, perhaps hundreds of kilometers wide, that collects hydrogen atoms from the interstellar medium as it travels. This hydrogen is then fed into a fusion reactor to produce thrust. In theory, this solves both the acceleration and deceleration problems because you never run out of fuel. The interstellar medium itself is your unlimited fuel tank. However, detailed analysis over subsequent decades has revealed severe problems. The interstellar medium contains only about 1 hydrogen atom per cubic centimeter on average. To collect enough hydrogen for useful thrust, the scoop would need to be impossibly large. Worse, the electromagnetic scoop itself creates drag as it interacts with the medium. Calculations by various researchers, including a key analysis by Daniel Whitmire in 1975, showed that for many configurations, the drag created by the scoop exceeds the thrust produced by the fusion reactor. The ramjet would actually decelerate you rather than accelerate you. This sounds like it might be useful for stopping. But the deceleration is uncontrolled and accompanied by tremendous heating and stress. More recent analyses have suggested that hybrid approaches might work. Use a Bussard-type scoop, not for fusion fuel, but simply as a drag brake at high speeds, collecting interstellar medium particles and deflecting them without attempting fusion. This is essentially a variant of the magsail concept, using electromagnetic interactions with the medium for passive deceleration. A fifth approach involves pre-positioning deceleration infrastructure at the destination before your main spacecraft arrives. The idea is straightforward. First, send a robotic probe that does not need to stop. It flies through the destination system at high speed, but deploys autonomous systems as it passes. These systems might include laser arrays powered by solar panels, magnetic decelerators, or orbital infrastructure. Over subsequent decades, these systems build up into a deceleration station. Then, when the main mission arrives, the pre-positioned infrastructure helps it slow down. This concept is actually considered one of the most realistic paths to interstellar travel by many researchers. It requires patience, decades of waiting between the precursor mission and the main mission, but it sidesteps the fundamental physics problem by shifting the energy burden to infrastructure at the destination rather than fuel carried from home. The main disadvantage is timescale. You need to send the precursor mission, wait for it to arrive, wait for it to build infrastructure, confirm the infrastructure works, and then send the main mission. For a trip to Alpha Centauri, this might mean the first humans or payloads do not arrive until 50 to 100 years after the initial robotic flyby. Now let us shift our focus to a different aspect of the stopping problem, one that becomes relevant at the extreme speeds we have been discussing. When you travel at a significant fraction of the speed of light, the physics of stopping becomes even more complex because of Einstein's special relativity. We need to examine how relativistic effects change the stopping equation. In Newtonian physics, momentum is simple. Mass times velocity. Double the velocity, double the momentum. Double the momentum required to stop. But Einstein showed that this is only an approximation valid at low speeds. At speeds approaching light, momentum is given by the formula P equals gamma times m times v, where gamma is the Lorentz factor, defined as 1 divided by the square root of 1 minus v squared over c squared, where c is the speed of light. The Lorentz factor is 1 at rest and increases toward infinity as speed approaches light speed. At 10% of light speed, gamma is about 1.005. The relativistic correction is small. At 50% of light speed, gamma is about 1.15. At 90%, gamma is about 2.3. At 99%, gamma is about 7.1.